Okay, Assalamu alaikum. Let's begin then. So we started vectors in our last session. We did some very basic concepts in the last session. Today we will do the relatively more complicated ones. So we started with the basic idea of vectors. Vector is something that's represented by both magnitude and direction. So it has a numerical value and it has direction. How do we represent vectors? There are different ways to represent vectors. One is using this arrow diagram. This represents the vector AB. A is the starting point and B is the end point. You can also represent the vector like this, AB vector, where A is the starting point, B is the end point. Remember, this arrow on top in this representation is important, because if you just write AB without that arrow on top, that does not represent vector AB, that just represents the length AB. Okay, that would not be a vector if you don't put an arrow there. So this notation is important. If it just says OB somewhere, understand they're not talking about the vector, they're talking about the length. Okay. If they're talking about the vector, they will always have this arrow on top. Then we talked about the concept of column vectors, that we can represent vectors in the form of column vectors like this. So we can have a vector which has two numbers written like this, x component and the y component. The first number represents the x component. If that's positive, that means you're moving to the right. If it's negative, you're moving to the left. If the y component is positive, you're moving upwards. If it's negative, you're moving downwards. All right. Then we talked about how to represent all of these different vectors. We looked at these examples. For instance, this vector mn on the right side. What's this? You're going from m and you're going to n. Now, in that process, how many units are you going left, right, or up and down? You're going 3 units left. That means the x component here should be -3. And you're going 4 units up. That means the y component here, it has to be 4. So that's what the vector mn looks like in column vector form. That's what we discussed. Then we talked about the magnitude of a vector. That tells you the length of a vector, right? So if you have a vector 4, 2, for instance, that means you're going 4 units up, right, and then 2 units up. What's the magnitude of this vector? You can find this using Pythagoras, right? You have two sides of a right angle triangle, x component, y component. You can just square them, add them, and then take square root. Using Pythagoras, you can find the length of this vector. So this is the formula that we use for that. If you have a vector x, y, the magnitude is given by this square root of x squared plus y squared. Okay, we did some examples in this. Sometimes you have the vector given and you have to find the magnitude. This is the notation that we use for that. Two vertical lines around the vector that represents the magnitude of a vector. This is how we can find this. Sometimes you're given the magnitude and you have some missing information in the vector. For instance, in this example, we were given that the magnitude of the vector PQ is 13. And given that information, we had to find the possible values of Q such that PQ vector was this -5 in Q. Okay, so what we did was we found the magnitude of PQ in terms of Q, and we equated that to 13 and found the possible values of Q from that. We got plus or -12 from that. Then we talked about these simple examples in which we have two vectors that are parallel and they have the same length. For instance, if we have a parallelogram that looks like this, PQRS, it's a parallelogram. In this parallelogram, if you know this vector 3b, then the vector QR is going to be the same as that as well. Okay, QR is also going to be the same because it is in the same direction, it is parallel, and it also has the same length as that. When two vectors have the same length and the same direction, they are said to be equal to each other. All right. So PS vector, it was 3b. QR has the same length and it has the same direction. We say it would also be 3b. Similarly, PQ vector and SR vector, they're parallel and equal. That means this here should also be 5 times it. Okay. So for two vectors to be equal, both of these conditions have to be met. They must have the same length, they must have the same magnitude, and they should have the same direction. Their length should be the same and their direction should also be the same. Both conditions have to be met for the vectors to be equal. Only the length being equal is not enough. Only the direction being equal is not enough. Both of these things have to be the same. If we have an equilateral triangle like this, so it's an equilateral triangle, all sides of this triangle are equal, which means PQ equals QR, which equals PR. Now, these are lengths, right? We don't have vector signs on top of them. These are lengths. The lengths are all equal. However, when we talk about vectors, PQ vector, QR vector, PR vector, these vectors all have different directions. Even though their magnitudes are going to be the same, since they have different directions, they are not going to be equal. So we cannot say that PQ or QR or PR, they're equal to each other. None of them is equal to each other. Okay. So these vectors are going to be different. Their magnitudes will be the same, but the vectors will be different because the directions are different. All right. And then we talked about addition of vectors, how we can add vectors. For instance, if we have a triangle like this, the vector AC is equivalent to saying AB plus BC. Okay. So in vectors, if the starting point is the same and the end point is the same, the vectors are equivalent. So for instance, if you want to go from A to C, one path that you can follow is that you can say, let's go directly from A to C like this, and that is the vector AC. You can also go from A to C like this. You can say, let's go from A to B and then B to C. That will be equivalent. So AB plus BC is equal to AC. You could also follow some other path, any other random path. So let's say there was a point D here. Okay. And then if you go from A to D, and then you go from D to C, this is also the same thing as AC. All right. So if the starting point is the same and the end point is the same, then the vector is the same. Okay. Now, the important thing to note here is the end point of one vector, when you're adding two vectors, the end point of the first vector and the starting point of the next vector, we call them head and tail, head of the first vector and tail of the second vector, they should be the same for this addition to work. So AB plus BC, that can be written as ACY because B are both the same, right? Similarly, we can say PQ plus QR, that equals PRY because Q is the same, Q is common between them, right? So we can add them like this. Similarly, if we can add multiple vectors as well, more than two vectors as well. If you have WX plus XY plus YZ, X and X, they are the same. Y and Y are the same. That means it's equivalent to saying if we're going from W to X and then from X to Y and then from Y to Z, that is equivalent to saying we are going from W to Z. So that's WZ vector. All right, that's how we can add vectors. And then finally, we talked about negative vectors in a question that we did. While we were doing a question, we talked about negative vectors as well. That if we have a vector AB and we have another vector which is the same length, the same magnitude, but it's in the other direction. These two vectors are supposed to be negative of each other. These two vectors are supposed to be negative of each other. If one, for instance, is 2p, then the other would be minus 2p. Okay, so these are negative vectors. All right, so that's what we talked about as well. Now, using all of this, what you can now do is you can find some missing vectors in any diagram. So for instance, if I had something like this, let me make a figure here. Let's say I have a diagram that looks something like this. It's a trapezium, and the shape of the trapezium is like this. Okay. And we know some vectors in this trapezium. Let's say this is P, this is Q, this is R, and this is S. All right. We know that SR is, for instance, 4 times A. This is 3 times A. This vector may be 3 times B. And this is another vector. Let's say this is 4 times, or let's say 3 times C. We have these vectors. And now we have some other points. For instance, we have this point P here, and that's the midpoint of QR. And we have another point on the base here. Let's say this is PQRST. Let's use another letter here. Let's call this X, and let's call this Y. X and Y are midpoints. X and Y are midpoints of QR and SR respectively. Okay, so these two points are midpoints on these lines. Okay, so that's the information that we have. And now what if we had to find the vector SQ, for instance? How do you find that? SQ vector. So what does that mean? The starting point of this vector has to be S. So we have to start at S. And the end point has to be Q. So we start at S and then we end at Q. What path can we follow on this diagram to go from S to Q? Now, there could be multiple paths that we could follow here. There are multiple ways of writing this down. One way to do this could be that you go from S to R and then from R to Q, right? That's one possible way of doing this. Another possible way of doing this could be that you go from S to P and then from P to Q like this. Or it can actually reduce the number of different unknowns. What I do is I'll make a parallelogram instead. So we have less variables and that will make it more clear. So let's say we have the same points, P, Q, R, S, the same way. Let's say we have P, Q, R is like this. And we have points like this. There is a point X here, and there's a point Y here. And we know that SR, this complete vector is, let's say, 4 times A. That's what we wrote earlier. And let's say this is 3 times B. And now that will also ensure that the opposite vectors are the same. Okay, so we have a situation like this. We have a parallelogram like this. PQR is parallelogram, in which we know one vector SR that is 4 times A, and we know another vector SP that is 3 times P. We have these two vectors given on this parallelogram. And we know that X and Y are midpoints of X and Y are midpoints of QR and SR respectively. That's the situation that we have. Now, how do we find the vector SQ? SQ means we have to go from S to Q somehow, right? S is the starting point and Q is the end point. We have to start at S and we have to end at Q. Now, what path can we follow on this diagram that takes us from S to Q and we know the vectors on that diagram, on that path? Now, first of all, let's mark the vectors that we know already in this diagram. Since the vector SP is 3B, what does that tell us about the opposite vector, this complete vector, RQ, what is that going to be? It's parallel and equal. That's a parallelogram, right? This is also going to be 3b. And similarly, if this vector is 4a, the vector on top there, that is also going to be 4a. Okay. Now, what path can we follow to go from S to Q? One possible path that we can follow is that we go from S to R and then from R to Q. That's one path that we can follow. So we can say SQ equals SR plus RQ. Now, what's SR? SR is 4 times A. And then from R to Q, that's 3B. So this becomes 4A plus 3B. Now, you could also go from S to Q in another way. You could also say SQ is SP plus PQ. You could also do that. SP plus PQ. Now, what's that going to be? SP is 3B. And then PQ is 4A. And you get the same thing from that, 3B plus 4A, 4A plus 3B. These are both equivalent. So that basically means we can follow any path on the diagram to go from one point to go from the starting point to the end point, and we would get the same result from that. Okay, no matter what path we follow. Now, what about vector Sx, for instance? If we had to find the vector Sx, what would that mean? Sx. So we want to start from S and then end at the point X. Sx, that is what we're looking for. How can you find this now? Again, find a path on the diagram that takes you from S to X. The starting point should be S and the end point should be X. So you go from S to R and then R to X, right? That's one path that you can follow on this diagram. So you can say S X is the same thing as SR. You go from S to R, and then you go from R to X, right? That's the path that you can follow. Now, do we know SR? Yes, that is 4 times A. But the problem is, we do not know what Rx is. We know that the full vector is 3 times B. But Rx, that is something that we do not know. Now, since we know that X is the midpoint, we know X is the midpoint of this line, that means this vector is basically going to be half of this complete vector, right? Because that will be half the length. Direction is the same, but it's half the length. What that means is Rx can be written as 1 over 2 half of RQ, right? Half of RQ. Well, what's RQ? RQ is 3B. So we can say it's half times 3B, and the vector Sx turns out to be 4A plus 3 over 2 times B. That's the vector Sx. All right. Now, you can think of another path to follow on this diagram as well, and that will give you the same result. Or that might be a bit longer, but that's also possible. You could also go like this. You could go from S to P, and then from P to Q, and then from Q to X. That will give you the same vector at the end. Okay, so you would do 3B plus 4A, and then QX, what would that be? It's in the opposite direction, number one, right? It's opposite to RQ. So we would say it's going to be negative. And then half of 3B, QX vector would be minus half of 3B, negative 3 over 2 times B, right? That's what QX would be. If you add these three, 3B plus 4A minus 3 over 2B, you would get the same result as this from that as well. Okay, so there's not going to be one unique path that you always have to follow. You can do any of the path. You can follow any path on the diagram, and that will give you the correct result. Okay, some will be more efficient than the other. Then the others, you would have to identify what's the shortest part that you can find on which you know all vectors. That will simplify things for you. Let's take another example. Let's say we want to find the vector y q, let's say yq vector. How do you find this now? We have to start at y and end at q somehow, right? Again, what's the path that we can follow on this diagram? that takes us from Y to Q. We can go from Y to R, and then we can go from R to Q. That's one possible path that we can follow. So we can say this is going to be YR plus RQ. Okay. What's YR? Y is the midpoint of that horizontal line. This complete length is 4 times it. What about YR? It's half of that. So this is going to be 2 times A. 4 over 2, that's 2. So this becomes 2A plus RQ. We know RQ is 3B. So it becomes 2A plus 3B. That's the vector YQ. All right. Let's do one last on this one. And then we'll do some more complicated ratios. Let's say we want to go from R to P. We want to find the vector RP. What's this vector going to be? We want to start at R and end at P now. So we want to go from R to P. What path can we follow on this diagram? We can either go RQ and then RP. That's one possibility. Or we could go like this, RS and then SP. Any of those paths will work. Okay. RP, let's say we go from R to Q and then from Q to P. That's one path that we can follow. Okay, what's RQ? RQ is 3 times B. So we can write that here, that's 3 times B. What about QP? Do we know what QP is? The vector that we know is PQ in this direction. This vector is 4 times it. If we want to do the opposite of that, that means QP. So instead of going from P to Q, we want to go from Q to P. This is going to be negative of that, right? So this becomes minus 4A. So it will be 3B minus 4 times A, right? Because we're going in the opposite direction here. This has to be negative 4A. And that gives us the vector RP. That's what we were looking for. Okay, so that's how we can find some unknown vectors in a situation like this. Now, these were relatively simple examples because we only had the midpoint, right? But sometimes you get more complicated ratios. Let's do some examples of that. So I've taken this from the worksheets. These are actually past paper questions. Let's have a look at some of these now. ABCD is a parallelogram. X is the point on BC such that BX ratio XC. X is the point BC such that BX ratio XC is 2:1. Now, whenever you have something written in the ratio form, I would recommend that you write it in a fraction form that will make it easier to understand. And this is how you would write it. BX ratio XC, you can say BX over XC. That is 2/1. If BX is 2, then XC is 1. Now, they've shown this point on the diagram as well. This is the point X, right? They've shown that in the diagram. If BX part is 1, then XC, if BX part is 2, then XC part would be 1. That's the ratio that we have. Okay. And what that means is, how many parts do we have in total from B to C? These are 3 parts in total. Okay. These are 3 parts in total. Now, this is very important to understand. These are 3 parts in total. BX is 2 out of 3 parts. XC is 1 out of 3 parts, right? We have 3 parts in total. BX is 2 out of 3 and XC is 1 out of 3. Okay. All right. Now let's look at the other information that we're given there. AB is 2P and vector AD is 3Q. We need to find in terms of P and Q vectors AC, AX, and so on. Okay, let's start with this one first. AC vector. What is this going to be? We have to start at A, end at C. We can go like this, 2P, and then go like this, 3Q. All right. So AC is going to be AB plus BC. Now, you don't always have to write this specific step in your exam. You can write down the vectors directly as well. It's for your own understanding, for your notes, that what exactly are we doing. If you want to go from A to C, we're saying, let's go from A to B and then B to C. What's AB? AB is 2P. What's BC? BC is parallel to AD. BC is parallel to AD. So that means this complete vector is therefore going to be 3 times Q. Okay. So we can say this is 2P plus 3Q. This is 2P plus 3Q. That's what we write down there. AX vector. We have to start at A and end at X. Okay. Now, what path can we follow on this diagram? We can go from A to B and then B to X. AB plus BX. Okay. Now, do we know AB? Yes, we know AB. AB is 2P. But the problem is we do not know what BX is. How do you figure that out? Now, AD vector was 3Q. That means this complete vector was also 3Q. So we can write 3Q here. And now we know the ratio between these two. This is 2 and this is 1. Which means if that total was 3Q, then BX part is supposed to be 2Q and this part is supposed to be 1Q. All right. So this is 2Q and that is 1Q. So BX, therefore, we say is 2 times Q. So AX turns out to be 2P plus 3Q. That's the result that we get from this. Okay. Again, that was slightly trickier than the previous one, but let's make it a bit more complicated now. Let's say we've got this now. We have this diagram in which X is the point on AB. X is the point on AB. Okay. AB is the line, is this line. X is some point on AB, where AX is equal to 1 over 4 times AB. Now they're talking about lengths here, right? But since they are in the same direction, we can say the same thing about vectors as well, even though here they're talking about the lengths. Why? Because they don't have these arrows on top. But since they are parallel, we can say that the vectors are also going to be in the same ratio because the directions are the same. All right. AX equals 1 over 4 times AB. Now, let's write it in proper form, and that will make it easier to understand. AX over AB. What is that? That is 1 over 4. That means if AX is 1, then AB is 4. Okay. If AX is 1, then AB is 4. What does that mean? If this length is 1 from A to B, if this length is 1, then what is the total length here? This is 4. What does that say about the vector? AB? AX vector was Q. What about AB vector? What would that be? We'll just multiply that by 4. So we can say from this, we understand the vector AB is therefore going to be 4 times Q. Right? That's what this ratio means. We know AX is equal to Q. AB is going to be 4 times that. So that's 4 times Q. Okay. Let's think about this now. AY is equal to 1 over 3 AC. Again, write it in proper form with only numbers on one side in fraction form and the lengths on the other side. AY over AC. AY over AC, what's that? That is equal to 1 over 3. What does that mean? If AY is 1, AC is 3. AY, if this is 1, AC is 3. Right? What does that mean? AY was P, then AC would be 3 times P. That's the vector AC. We just multiply that with 3 because if this is 1, this is supposed to be 3. All right. So we know that AY is P, then AC should be 3 times P. Okay, let's move on now. We've found those vectors. Z is the point on BC produced such that CZ is equal to 2 times BC. Okay, so BC produced means you extend BC outside like this, such that you have some point Z outside. And the condition is CZ equals 2 times BC. Again, to save yourself from careless errors, I would recommend you first write it in this form, in the proper ratio form, CZ over BC. What is that equal to? It's equal to 2. 2, we can write that as 2 over 1, right? If I bring BC to the left side, I get CZ over BC on the left. On the right side, I have 2. I can write that as 2 over 1. What that means is, if CZ length is 2, then BC is supposed to be 1. If this is 1, then this is 2. Okay? You could do it directly as well. That's perfectly okay. But if you standardize it like this for more complicated cases, you would see that it really helps. Okay, so that's what we know. If this is 2, this is 1, and that means in total, if there were 3 parts, this is 2 out of 3, and this is 1 out of 3. All right, now keep that in mind. Express as simply as possible in terms of P and Q x, y vector. Okay, so we have to start from x and end at y. X, y, this is the vector that we're looking for. How do you find this vector? We have to find a path on the diagram that takes us from the starting point to the end point. We start at x. We can go from x to a first, and then we can go from a to y. X, a plus a, y. That is going to give us the vector x, y. So we go from x to a, and then from a to y. All right. Now, what's xa? Xa is opposite of q. That's going to be minus q. Ay is p. So this becomes minus q plus p. You can say that's p minus q. This is the result that we have. You can write as minus p plus q. That's also minus q plus p. That's also fine. Or you can write p minus q. This is the vector that we were looking for. Now it says find the vector BC. So we start at B and end at C. Now on this diagram, we need to start from B and end at C, and we need to find this vector somehow. What path can we follow on which we know any vectors? Now remember, we have found the vector AB already. That's 4 times Q. And we've also found the vector AC. That's 3 times B. So in order to go from B to C, what we can do is we can say, let's go from B to A and then go from A to C. Okay, that's the path that we can follow. So BC can be written as BA, that we go from B to A, and then we go from A to C. All right. And now what's BA? BA is negative of AB, right? What would that be? Minus 4Q. And then AC is 3 times B. And that's the vector BC that we were looking for. That's 3P minus 4Q. That's BC vector. All right. Now it says find the vector XZ. XZ. How do we think about this now? XZ vector. So we want to start from X now and end at Z. We want to go from X to Z. Now, what path can we follow in order to go from X to Z, on which we know the vectors? We could say we go from X to Y and then Y to Z, but the problem is we don't know what YZ is, right? We know XY, but we do not know YZ, so that's not going to help. We know nothing about YZ, right? But we know something about this side. We know the ratios on that side, okay? What we can say is, let's go from, if we want to go from X to Z, let's go from X to B, and then we can go from B to Z, right? That is something that we can do. Let's do it that way. We say, let's go from X to B, and then go from B to Z. That's the path that we can follow. Now, do we know anything about this path? What about XB, first of all? What is that going to be? we know that this complete vector from A to B, that is 4 times Q. And this is just Q. What about this remaining vector? What is this going to be? If this is Q, this complete one is 4Q. This is just 3 times Q, right? That was the ratio. This was 1:3. So this is 1. This is supposed to be 3. So this is going to be 3 times Q, first of all, XB vector. And then we have to go from B to Z. What is that going to be? We know the ratio between these sides, right? This is 1 part, this is 2 parts, and the complete thing is 3 parts. Do we know any of these vectors? We know the vector BC. We found that in the previous part. BC vector is 3P minus 4Q. That's the vector BC. If we know the vector BC, if we know this part, what is the complete vector going to be? That's 3 parts. We just multiply BC by 3, and that is going to give us the complete vector BC. So that's what we do. We say it's going to be 3Q plus 3 times BC, right? BZ is 3 times BC. So we say that's 3 times 3P minus 4Q. We can simplify this and see what that gives us. 3Q plus 9P minus 12Q. And that simplifies to 9P minus 9Q. That's the result that we were looking for. It's 9P minus 9Q. That's the vector XC. Does that make sense? Any problem with this? All right. Now we want to find the ratio XY to YZ. Now they're not talking about vectors. They're not talking about vectors. These are lengths, right? X, Y, and YZ. X, Y, and YZ. Now, in this case, since they're parallel, it could be the same ratio for the vectors as well, and that's all right. How do you find this ratio XY to YZ? That is what we are looking for now. Okay, now how do we think about this? We know the vector XZ. We have found that. XZ vector we have found. And we also know the vector XY. We found that in the beginning. XY was P minus Q. Right? Let me write both of them down here. XY vector was P minus Q. XZ vector is what you've just found. XZ vector is 9P minus 9Q. Can you find a relation between these two vectors first? If we multiply XY by 9, you get XZ, right? Multiplying P minus Q with 9 gives you 9P minus 9Q. So the relation between XZ and XY therefore is that XZ will be 9 times, or you can write it like this. You can say XZ over XY, that is 9 over 1, right? That's the ratio between XZ and XY. If XZ is 9, XY is 1. Is that what they're asking for? No, they're asking for XY and YZ. Okay. Okay, XY is written first there. If I write XY first, it will be XY over XZ. That's 1 over 9. Okay, that's the ratio between XY and XZ. But they want the ratio between XY and YZ. Now let's go back to the diagram. We have figured out if this is 1, then this whole thing is 9. That's the ratio that we have found. If that small part is 1, then that whole thing is 9 units. That's the ratio between XY and XZ. What about YZ? If this complete part is 9 units and xy is 1 unit, then how many parts would yz be? Yz would be 8 units, right? If the total is 9 units and this is 1, then this is supposed to be 8. So the ratio between xy and yz, therefore, that becomes 1:8. So this becomes 1:8, and that's what we write here. The ratio is 1:8. Okay. With xz, it's 9. With yz, it's 8. It's 1:8. Make sense? Any problems with this? Okay, now let's move on. Let us move on to the next concept. Okay, now they want you to understand this terminology called position vectors. Position vectors. What are position vectors? It's a simple concept. If you have a point on this xy plane like this, let's say we have x and y axis like this, and there's a point, let's say somewhere here, this is point A. It has coordinates 4 and 2. Okay, so this x coordinate is 4 and the y coordinate is 2, and this is the origin. Right? Now we call 4 and 2 the coordinates of the point A. Right? We can think of this point in the form of a vector as well. Basically, we say, how can we start from the origin? How can we start from the origin and reach that point A on this diagram by moving some units horizontally and some units vertically? So how do I go from origin to that point A? I can go 4 units to the right, and then I can go 2 units up. So the vector OA, what would that be? Vector OA. How do I go from O to A? I have to go 4 units right, and then I have to go 2 units up. So that vector becomes 4, 2. This OA is known as the position vector. It's the position vector of the point A. Okay. So essentially, whatever are the coordinates of a point, if you write them in vector form like this, write them in vector form like this, it becomes the position vector of that point. So this is the position vector of the point A. If I have another point somewhere, let's say there is this point here on the left side, and this point has coordinates -5 and 1. This is -5 and this is 1. How can I start from the origin and reach that point? I have to go 5 units left and then 1 unit up, right? 5 left, 1 up. What would that be? OB vector. That would be -5, 1. This is the position vector of the point B. Okay. Why is this the position vector? Because it's basically telling us the position of the point with respect to the origin. That from the origin, how can we reach that point by moving some units horizontally and some units vertically? How many units do I have to go left, right, and how many units do I have to go up, down to start from the origin and reach that point? That's the position vector. So it's essentially the coordinates of the point written in vector form. Okay. Now, using position vectors, what you can do is you can find the vector AB now, for instance. Now, how do you go from A to B? If I wanted to go from A to the point B, how can I do that? Now, in this case, I have the diagram given. So using the diagram, I can easily figure out, okay, this is 4 and this is -5. So I have to go like 9 units to the left. So that would be -9, and then I have to go 1 unit down, so that's -1. That's what the vector AB is going to be, because we have the diagram given. But if we don't have the diagram, what we can think of this is, since we have these two vectors given, so we know that OA is this and OB is this. So let's say we have these two vectors given, OA is 4, 2, and OB is -5, 1. In order to go from A to B, using these two vectors, what we can think of is, let's go from, so we have these two vectors given, right? We have OA and we have OB. These are the two vectors that we know. OA and OB. These are given to us. Now, using these vectors, how can I find AB? I can say, let's go from A to O. That's AO. And then go from O to B, right? That's the path that I can follow. AO plus OB. Now, do I know what AO is? No, I know OA. I don't know what AO is. But OA is just negative of that. So I can say this is negative OA plus OB. And then if you rearrange this, you get OB minus OA. AB vector is equal to OB vector minus OA vector. And that basically tells you that if you have any vector, you can write that vector in terms of the position vectors of the points that that vector is coming from. So for instance, in this case, we are looking for the vector AB, right? The vector AB can be written in terms of the position vectors B and A. Position vectors of B and A. What exactly are we doing here? We are saying AB vector is going to be equal to the position vector of the second point position vector of the second point. So AB vector, in which in this the position vector of the second point is OB, right? This is the second point, B, minus the position vector of the first point. Minus the position vector of the first point. That is how we can find the vector AB. It's OB minus OA. All right. And that's a general rule that we have now. This is the logic behind it, that we want to go from from A to B. We can say that's AO plus OB. AO can be written as minus OA, and then that becomes OB minus OA. That's a general rule that you can remember now. That will really help you in a lot of calculations. That whenever you have a vector, let's say PQ, or any vector, and you want to write that vector in terms of its position vectors, in terms of the position vector of P and Q, that's OP and OQ. How can you write that? It will be position vector of the second point minus the position vector of the first point. Okay, that's what you need to remember. It's not OP minus OQ, it's OQ minus OP. If you had MN, what would that be? ON minus OM. Okay. If you had XP, for instance, what would that be? OP minus OX. So any vector can be written in terms of the position vectors of the point that that vector is made up of. All right. I hope that makes sense. Now, let's take an example on this. Let's say we are given that there is a point C and it has coordinates. There's a point A, it has coordinates -7 and 3. And there's a vector AB, which is 5 and 6, 5 and let's say -6, we need to find the coordinates of the point B. Now, given this information, how can you find the coordinates of the point B? That's the problem. Okay. So we have the coordinates of the point A given. We have the point, we have this vector AB given. And we want to find the coordinates of B, for instance. How can you find them? One way to do this could be that you say, this is A. We can write this as OA, right? OA is going to be -7 and 3. And we have AB vector, that is 5 and -6. How can we write AB vector in terms of its position vectors? We can say AB is equal to OB minus OA, right? AB vector is OB minus OA. What we can do is, we can rearrange this. Since we're looking for B, we can say that means OB equals OA plus AB, right? If we remember this, we can just rearrange that every time to make an equation in which what we want is the subject. And now OB can be found like this. That's OA, which is -7, 3, plus AB, which is 5 and -6. And OB vector turns out to be -2 and -3. So that means the coordinates of B therefore are -2 and -3. We can write them in coordinates form because that's what they're asking for. The coordinates are -2 and -3, and that's what we were looking for. So using position vectors, we can find some missing points like this. Any problem with this? No? Okay, now one last thing. And that is showing that two vectors are parallel. Okay. Parallel vectors. How do we know that two vectors are parallel? Now, this is something that will require some more practice. We'll do that tomorrow. I'll give you a quick introduction to this today, and then we'll do, we'll basically revise it tomorrow and also do a lot of practice questions. Tomorrow means on Thursday, right? Whenever we have our next class. Okay, parallel vectors. What are parallel vectors? Let's say I have two vectors. One vector is AB, and it has these components -4 and 7. And there's another vector BC, and that is -12 and 21. And we need to determine whether AB and BC are parallel. Whether AB and BC, they are parallel vectors. That's what we need to figure out. Okay. Now, it's not necessarily that it's BC. It could be as in, it's not necessarily that the point B is common. Let's say it could be CD as well. But it's any other random vector. How do we show that these two vectors are parallel? The way to do this is, let me write that down here. The condition, two vectors are parallel if one can be written as a multiple of the other. As a multiple of the other. For instance, if we have these two vectors, A, B, and C, D, if they're parallel, we should be able to write them in this form. If they're parallel, AB can be written as some constant, let's say K times CD, or the other way around, CD is equal to K times AB. If we can write the vectors in one of these forms, then that means that BC and C, that AB and CD, they're parallel. Okay. So if AB can be written like this, or CD can be written like this, that means AB and CD are parallel. Okay. If we can do this, then these vectors are parallel. That's the idea of parallel vectors. Now, this is one way of doing this. Now, let me apply this in this example. This is one way of proving that two vectors are parallel. If one can be written as a multiple of the other. Now, in this case, think about it. Can you multiply one of these vectors with some number to get the other vector? Take any one of these vectors and see if you can multiply it by some number to get the other vector. Generally, it's easier to think of using whichever vector has smaller numbers. So this vector, the first one, has smaller numbers. Can we multiply it by anything to get the other vector? If I multiply this vector by 3, that will give me 3 times minus 4, which is minus 12. 3 times 7, that's 21. So yes, I can say that CD vector is equal to 3 times AB. I can write it like this, right? CD is 3 times AB. If I were to multiply AB by 3, I would get CD. And that means that CD and AB, they are parallel to each other. Okay, that's one way to prove that two vectors are parallel. Right, I can multiply this by 3 to get the other one. Another way to think about parallel vectors is we could also do something like this. We could say if the ratios of corresponding components are equal, of the vectors are equal, they are parallel. It's mostly going to be an easier way of doing this. Let me explain what I mean by this. If the ratios of corresponding components of the vectors are equal, then they're parallel. Let's take an example. If you have a vector xy and you have another vector ab, let's say the first vector is p and it's represented by xy. This is vector, and there's another vector q, which is, let's say, ab. So for example, in these two vectors, if x over a, divide corresponding components, x over a. If x over a, it equals y over b. Y over b. Then that means these vectors are parallel. And vectors p and q are parallel vectors. Okay, if the ratios of the corresponding components are equal, then they're parallel vectors. That's one way of doing this. Another way to think about this is also that when you have a vector xy, for instance, remember this is the x component, this is the y component. So the vector goes like this. If you have a vector like this, it has some x component and some y component. This x component, this is y component. If you do y component over x component, that's basically change in y over change in x. You can also find the gradient using this. Y over x basically gives you the gradient. Let me add that here. That's actually an important thing that I just thought of. Gradient of a vector. Finding gradient from a column vector. So let's say vector AB is equal to 4 and minus 3. Then the gradient of AB would just be the y component divided by the x component, right? Because y component is basically giving you the change in y, and the x component is giving you the change in x. So gradient of AB would be minus 3 divided by 4. That will be the gradient of AB. You just divide the y component by the x component, and we can generalize this. This is a specific example, but we can generalize this that whenever we have a vector in this form, if AB vector is x, y, then the gradient of AB, that is given by y over x. That will be the gradient of AB. We just divide the y component by the x component, and that gives us the gradient of that line. Okay. We could use that here as well. If two vectors are parallel, that means their gradients should be the same, right? The gradient should be the same. So you can also think of it this way, that y over x that should also equal b over a, right? Because they're the gradients y over x, that equals b over a. And you see, that's the same thing. If you rearrange this, you can bring x here and then take b to the left side. So b over a equals y over x. The gradients are equal. You can also think of it this way. Okay, both of them work. So that's another way of proving that two vectors are parallel if their corresponding components, if their corresponding ratios are equal like this. All right. That's another way of showing that two vectors are parallel. So in this case, for instance, we could do that as well. We could say AB and CD are parallel. Using this as well, I can say gradient from this, that's 7 over minus 4, equals gradient from this, which is 21 over minus 12. If they're both equal, we get minus 7 over 4 equals minus 7 over 4. They're both equal. That means they are parallel. Okay. That's another way of thinking about this, that we just divide the ratios of the corresponding components. And this is something that we'll find really helpful in more complicated examples. We'll do some examples tomorrow, but there's another terminology that you will see being used. If it says 3 points are collinear, okay, I'll go over this again tomorrow as well. If you're given that points A, B, and C are collinear, what does collinear means? Collinear means they lie on the same line. They lie on the same line. If the 3 points A, B, and C, they lie on the same line. Then if we take 3 points on this line like this, let's say we have point A here, we have another point B here, and we have another point C here. We have a line in which we have 3 points A, B, and C. If they say something like this, the 3 points are collinear or they lie on the same line. What that means is vectors AB, so I can have this vector AB, vector BC, this vector, and vector AC, this complete vector. They are all going to be considered parallel to each other. Parallel means they have the same direction, right? They have the same direction. So if you have 3 points that lie on the same line, what you can do is you can take any combination of them, AB, AC, BC, they will all be parallel. Parallel means that the ratios of their corresponding components are going to be equal like this, or one of them can be written as a multiple of the other, right? All of these conditions, they apply on them. If 3 points are on a straight line, that means these all vectors are going to be the same. They're going to be equal to each other. Okay, that's another thing that you will keep in mind while attempting questions. Now we will do some practice questions on this in the next class, inshallah. And this is something that I will review in the next class quickly as well, the concept of parallel lines, parallel vectors, and the concept of collinear points. Okay, and we'll do some practice questions on this in the next class. Review this before we come back for the next class, and also attempt some questions from the worksheets that are added to OneNote. I'll try that I upload them to a classroom by tonight as well. But they are available on OneNote already, so you can have a look at them, attempt some questions from this, and now you should be able to figure out most of them. But we'll spend the next class on doing practice questions on this, inshallah. All right, so that's it for today. I'll see you again in the next class.